Hello again and welcome. We're continuing on with the very first of the intermediate math competitions, the Cimc, put out by the Cemc. We're doing part B. We've made it all the way through just the short answer, part A, give us what you got, put it in the little box provided in the booklet. Now we're doing part B, so we're going to have to justify our answers. Okay? So let's take a look at the very first question in part B. So what have we got here? So for each question, part B, you have to explain and justify, that sort of thing. If you very poor with your presentation, if you do something inelegant, you might not earn full marks, that sort of stuff. So question number 1, we have 4 figures, figure A, figure B, figure C, and figure D. Each of them is, the circle has center O. Okay, well, in A, B, and D, we have the circle with center O. They don't mention C yet. Alright, so question part A. Determine the area of the shaded region in figure A. So right here we have O as the center, we have a radii of 2 apparently, and we're asked for a quarter of the circle. How do we know it's a quarter of the circle? Because we're asked for this little 90-degree section, 360 degrees in a full circle, so we're asked for a quarter of a circle. Let's just draw a little picture of the circle to remind ourselves, that way we don't have to keep going back. So there's a formula for this kind of area. If you want a section, or sort of a pie slice of a circle, and you're given the sort of the angle of the pie slice, so in our case it would be 90 degrees, there's a formula. And that area is theta degrees over the full 360 degrees times pi r squared. So for part A, theta is 90. Pi r squared, and we know what r is. It's a radius of 2. So we can simplify that to 1/4 pi. 2 squared is 4. So the area is pi. There's no meters squared or anything like that in the question. We're just simply asked for the area. So we get an area of pi. That's question part A. Now part B. Determine the area of the shaded region in figure B. So figure B up here. We've got the same sort of right angle, but now we're sort of just asking for this little sliver up here. Okay? We're basically omitting this entire right angle triangle, this isosceles right angle triangle. So once again, we'll draw another little picture of what we're talking about. And we have right angle. Still radiuses of 2, so it's basically the same circle as before. We're just asked for a different shaded area. Oops. So this little sliver here is the same as taking the quarter chunk we found from part A and subtracting off the area of this triangle here. We already know what the quarter slice of the circle is in terms of area. It's pi. So if we figure out what the area of the triangle is, we'll be able to subtract the two and get the area of this little sliver. It's a right angle triangle, and it's isosceles. Both of these legs, both of these sides are 2. So we want 1/2 base times height. Well, the base is 2, the height is 2. So we're going to get a final answer 2 for the area of this triangle. So the area of the shaded region, it's pi, because that was the quarter slice, minus 2, because we're omitting the triangle of size 2. Okay. So that gives us question part B. So now we're on to the question, the part C of the question. In figure C, we have a triangle PQR. It's equilateral and it has a side length of 2. We only need to specify one side length because equilateral triangles have the same side lengths for each side. They also have the same interior angle at each point. It's going to be 60. So determine the area of triangle PQR. Okay. So let's go back to our little sketch pad. In the diagram that they provided in figure C, they actually provide us the height that we should be looking for. So I think it was PQR. And they gave us this little line here, meeting down here at T. And this is the height that we would want. If we could figure out what this base is and what this height is, we'd be able to figure out the area of the triangle. We know the side lengths are 2. So all the side lengths are going to be the same. Okay. I can't remember. Did they give us any more information? Nope. So we just have to figure out the area from all that we have here. Okay. Now the height forms a right angle triangle here. Where does this point T lie? Well, he drops down from P and he meets QR at right angles, at the right angle. So we could make a symmetry argument, or we could make another argument. Really, any sort of argument would do, but we just want to know where T is. Actually, we don't even need that. We don't need to know exactly where T is. We can figure it out with trigonometry. So let's ignore all that. Because we know these angles here. So PQR, QRP, RPQ, all these angles are going to be 60 degrees. Just because it's equilateral. All the angles will have to be equal, all the side lengths are equal. It's a regular polygon. So then what do we have? So we have 60 degrees in here. So we can figure out angle QPT. 180 degrees minus the 90 degrees coming from angle PTQ minus 60 degrees, the angle TQP. Alright, so just need to use a little trigonometry. So if we wanted the height, we would have to do, if we use this 60 degrees here, we do opposite over adjacent, or sorry, opposite over hypotenuse, silly me. And that's going to be, sorry, opposite, not adjacent. It's going to be sine of the angle, of the angle at PQT. So sine is 60 degrees. We can figure that out either on our calculator or 30, 45, 60. These are very special angles that you should know and should probably have memorized for these contests. These sorts of triangles pop up a lot. We know this is going to be square root of 3 over 2. And since we know that PQ is equal to 2, we see our height, PT, is equal to the square root of 3. All right. The way I was going to do it before was I was just going to argue that QT is equal to TR, so each of these will have to be 1. And then I'd get a square root of 3 in here by using the Pythagoras theorem. But either or, trigonometry is fine because it's an intermediate competition, so grade 10 is certainly fair game. Trigonometry, fair game in this competition. So the area of PQR, that's going to be 1/2 base times height. So our base is QR times our height is PT. 1/2, 2 times square root of 3. So the area of PQR is the square root of 3. All right. Straightforward, simple enough. Just used a little bit of trigonometry there. Or you could use symmetry argument, or there's probably a couple other ways to figure out the area of that. I would caution against using something like Heron's formula or something like that. It seems overly complicated for a simple thing like that. Trigonometry seems the right way to attack that question. All right, D part. So, last part in question 1. Determine the area of the shaded region in figure D. Okay, so we just needed this little this shaded sliver. So it brings to mind part B. That is this one up here where we figured out this little sliver. And what did we do there? We figured out the area of this quarter slice, and we subtracted off this triangle. Okay. Well, this triangle in here is going to be exactly the same area that we just figured out in part C. So really all we need to do is figure out the size of this slice and what its area is. So let's draw ourselves a little picture again. There's O. Oh, that's an awful little picture. We'll just redo the whole thing. There we go. Diagram drawing, not always my forte, but you don't need to be getting out your compass and a straight edge every time you draw a diagram. It's only for your benefit that you have the diagram, so just make it legible for your purposes. So once again, we can find the area by finding the area of the slice. And subtracting the area of the triangle. Which we know is going to be root 3 from part C. So we just need to figure out the area of this slice, really. That's the only thing missing, and then we'll subtract off square root of 3. So we can notice that this triangle here is equilateral. So what does that tell us? We get an interior angle. Each one is 60 degrees, which means the one at O is 60 degrees, as are the other two. So if we use the formula mentioned in part A, we get the area of the slice. So 60 degrees over the total 360 degrees, so that's the fraction of the circle that we're going to try and find the area of, times the area of the circle. So 1/6 times the area of the circle, and that simplifies to 2/3 pi. So the area is going to be this slice. So that's 2/3 pi minus the area of this triangle that we figured out in part C. So 2/3 pi minus square root of 3. Let's just write that pi a little better. Right? There's no nice way to simplify this. We could probably get a common denominator of 3. So if you wanted to, you could write it like this. 2 pi minus 3 root 3 over 3. Honestly, I prefer this one, but you can go with this one as well. I don't. They're basically equivalent, and some people like having the common denominator when you're dealing with a fraction. But either or is fine. And we check. We finished part 1, or sorry, question 1 of part of the B part of the contest. Done all 4 problems. So now we can scroll down. We can move on to question number 2, which looks like it's going to involve embedded pentagons, but we'll explore that in the next video. So join me then. Thank you.